classroom of 30 students. Each takes a math test every month for a year. Some start strong and plateau. Others start slow and accelerate. The average trajectory across the class is useful, but it hides enormous individual variation. In pharmacokinetics, patients are the students. Drug concentrations are the test scores. Repeated measurements over time create the same structure. The classroom model, mixed effects modeling, handles both the population average and the individual deviations. If the same patient a drug and measure blood concentration at 8 time points, those 8 measurements are not independent. They come from the same body, the same metabolism, the same kidneys. If point 3 is high, point 4 is probably high too. Pooling all observations from all patients, as if they're independent, violates a fundamental assumption of ordinary regression. The correlation within patients must be modeled where your standard errors are wrong and your confidence intervals are too narrow. Fixed effects describe the population average. The average clearance across all patients, 0.15 milliliters per hour per kilogram. The effective body weight on clearance. Clearance increases with weight raised to the 0.75 power. The effective treatment. Drug reduces tumor volume by 30%. Fixed effects apply to every patient in the population. They're the facts about the class as a whole. Random effects capture individual deviations from the population average. Patient I has clearance 20% above typical, their personal metabolism is faster. Patient J has clearance 30% below, slower metabolism. These individual deviations are random effects, denoted eta. Eta is assumed to follow a normal distribution with mean 0 and variance omega squared. The variance omega squared is the inter-individual variability, the IIV reported in every PopPK table. The mixed effects model combines both. The observation Y for patient I at time J equals the fixed effect prediction based on dose time, and covariates, plus the random effect for patient I, their personal deviation, plus residual error epsilon, measurement noise and model misspecification. Fixed effects are estimated as single values. Random effects are estimated as distributions. The model is called mixed because it mixes both types. This is the foundation of NONMEM, NAMICAR, LIME, and every population PC analysis. Inter-individual variability, how much patients differ from each other. Clearance for patient I equals typical clearance times exponential of eta I. This exponential form ensures clearance is always positive and creates a log normal distribution. Inter-occasion variability adds a second layer. The same patient on different study visits might have slightly different pharmacokinetics, different food intake, hydration, compliance. Add kappa to the model, clearance on occasion J, for patient I equals typical clearance time exponential of eta I plus kappa ij. IIV is permanent. IOV is transient. Fixed effects for the population. Random effects for individuals. Repeated measures within each individual. The mixed model accounts for all 3 levels. Next, how to estimate what you can't directly observe.